I'm an English teacher by training. And the project that led to this architecture began with a classroom problem. I began building a system, the digital learning companion, designed to give students live feedback while they practice structured writing. Two constraints guided the work. First, the system needed to respect teachers' professional judgment. Teachers decide what counts as a claim, as evidence, as readiness for the student to move on to the next component. Second, the student record had to be protected from probabilistic interpretation. Generative AI can be very useful in analyzing text. But we cannot allow a probabilistic model to directly mutate a student's learning state. So the architecture had to support three things: live feedback for students, preserved authority for teachers, deterministic control of the student record. The design problem eventually led to a broader architectural idea. In any system like this, there's a moment when the system decides what happens next. In the system we designed, every consequential decision passes through a structured moment we call a turn. A turn binds three components: signals, measurements from the world, interpretation, evaluation of those signals, authorization, a policy deciding whether state may change. If authorization permits it, the system produces a new state. The turn records a snapshot of the decision moment, including the signals observed and the governing logic responsible for the decision. So the system evolves like this: state, turn, state, turn, state. Each turn records the logic responsible for the next state. Now let's take a look at a concrete example. Imagine a student writing a short argument. School should start later. In this architecture, the system observes signals in the student writing. Those signals might detect things like, is there a claim here? Do we see evidence? Is there a logical link? These signals become the inputs to interpretation. If a model is used at this stage, it does not operate directly on the student record, nor does it decide the system state. It only evaluates the signals that have already been defined. In other words, the model participates in interpretation, not authorization. That distinction matters. Because the model only sees bounded signals, its influence on the system is constrained and inspectable. It cannot directly mutate the student record. Interpretation evaluates the signals. Then, an authorization policy determines the next learning step. This moment where signals are interpreted and the system decides what may happen next, is a turn. The authorization policy determines the next step for the learner. It could be revise claim, strengthen evidence, go on to the next knowledge component. Only one next step is issued per turn. This discipline keeps the system simple and inspectable. This reasoning does not require AI. Because the primitives, claim, evidence, reasoning, are explicitly defined, the system can provide deterministic feedback to help the student practice. This also reduces the need for large amounts of student data. When the primitives are clear, the system doesn't need to know everything about the learner. It only needs to evaluate the work in front of it this turn. Structured writing is just one illustrative example. The architecture works the same way for mathematics, simulations, enterprise decision systems. What matters are primitives that reflect professional judgment. Once you look at the system this way, you see that system evolution is simply a sequence of turns. Each turn binds the logic responsible for the next state. So instead of thinking of a system as a series of state changes, we can think of it as a series of decisions. Those decisions become explicit objects in the system. Once decisions are recorded this way, something interesting becomes possible. We can isolate policy drift. If an authorization policy changes, we can identify exactly which turns were affected. Instead of guessing why the system behaved a certain way, we can trace the change to a specific decision boundary. Turns make system evolution inspectable. Once decisions are recorded as turns, the past becomes a policy laboratory. We can replay the same sequence of signals and interpretation under different authorization policies. Same signals, same interpretation, different policy, which produces a different state trajectory. Instead of debating policy changes abstractly, organizations can test them against real, historical decision sequences. Most systems we build today evolve through a series of state changes. But the decision responsible for those changes is buried in application code or model behavior. So when something unexpected happens, it can be difficult to answer a simple question. Which decision produced this state? Turn-based systems approach the problem differently. Instead of allowing state to change implicitly, each change must pass through a recorded decision boundary, a turn. That means the logic responsible for a state transition is no longer hidden in the system. It becomes inspectable, explicit, and versioned. This architecture can be summarized with 5 principles. State evolves only through turns. Signals measure the world deterministically. Interpretation evaluates signals. Authorization governs mutation. Each turn binds the governing logic. This architecture also clarifies how AI can safely participate in decision systems. AI can be extremely useful in interpreting signals, but in a governed system, AI does not authorize state mutation. Authorization policies remain explicit and versioned. This allows organizations to benefit from probabilistic reasoning while preserving control of consequential decisions. AI assists reasoning. Policy approves action. This also has another benefit. When decisions are structured this way, coordination becomes much easier. Humans, AI systems, and organizational policies all participate in a shared decision framework. So that's the idea behind the emergent state machine. At its core, it's a very simple shift. Most systems record what happened. An emergent state machine records the decision that made it happen. System evolution becomes reconstructible. Policy changes become testable. And the boundary between probabilistic reasoning and authoritative decision-making becomes clear. The work that led me here started in the classroom, designing a system to help students practice writing while protecting the integrity of the learning record. But the architecture isn't limited to education. Any system that combines probabilistic reasoning with consequential decisions can benefit from a clear decision boundary. The digital learning companion and the underlying architecture are open source. The DLC is a work in progress for anyone interested in inspecting the system, exploring how primitives function in a deterministic architecture, or building extensions or testing the ideas in other domains. I'd be very glad to hear from you. Thank you for taking time to explore these ideas with me.